The PHENIX collaboration has recently measured the modification of J/Psi yields in 3 collision systems involving small projectors, specifically He+Au, He+Au, and He+Au. These measurements provide a direct comparison of inclusive charmonium production for projectors with 1, 2, and 3 nucleons on Au target. The results are presented as nuclear modification factors, RAB, as a function of rapidity, which is a measure of the modification of J/Psi production in nuclear collisions compared to that in P+P collisions. The experimental setup used by PHENIX includes the muon arms, which are located parallel to the beam pipe and measure muons and unidentified charged hadrons at forward and backward rapidity. The forward vertex silicon detector, FVTX, installed in the PHENIX 2012 upgrade, covers the pseudo-rapidity range 1.2 less than eta, less than 2.2, providing the mass resolution necessary to extract the Psi-2s signal. The measured rapidity dependence of the modification for P+Au, P+Au, and He+Au, integrated over PT and for 0.100% centrality, is shown in Figure 1. The data are compared with model calculations by He+Au et al., which include only cold nuclear matter, CNM, effects. The forward rapidity data are well described for all 3 systems, as are the backward rapidity P+Au data. However, the backward rapidity P+Au and He+Au data are not reproduced by the shadowing calculation alone. An estimate of nuclear absorption, where the forming charmonium breaks up in collisions with nucleons that have not yet passed through the production point, has been folded into the shadowing calculation and is included in Figure 1. Including the absorption estimate brings the backward rapidity calculation into reasonable agreement with the P+Au and He+Au data. These results provide valuable insights into the effects of energy production on J/Psi yields in light systems, shedding light on the interplay between CNM effects and the possible presence of a deconfined medium in these systems. The findings are significant for understanding the nature of the quark-gluon plasma, a state of matter believed to have existed in the early universe and which is recreated in high-energy heavion collisions. The research paper discusses the nuclear modification factor of inclusive J/Psi as a function of the average number of binary nucleon-nucleon collisions, ENCOL, in P+O collisions, comparing it with the transport model. The results indicate that the J/Psi and Psi-2s nuclear modification follows a similar trend at forward rapidity, with no clear difference in suppression in the most central collisions. However, the Psi-2s shadowing predictions provided by He+Au et al. underpredict the suppression at forward rapidity, while the transport model predictions for both Psi-2s and J/Psi underpredict the suppression and describe the relative modification well, suggesting that the Psi-2s suppression in P+O collisions is consistent with final state effects. The paper also presents a preliminary result for J/Psi v2 using the PHENIX Run 14 Au+O dataset at square root SNN equals 200 JV. The PT-dependent J/Psi v2 measurements from PHENIX, STAR, and ALICE are compared, showing a clear non-zero v2 measured by ALICE, which is different from the PHENIX measurement that is consistent with 0 across all point bends. The systematic uncertainties were conservatively estimated, not taking into account cancellations or correlations of uncertainties from different sources. Additional data from Run 16 of RHIC will be included in the final results, and it is expected that both statistical and systematic uncertainties will be significantly reduced. The study highlights the importance of understanding the interplay between different quarkonium states in heavion collisions, particularly the J/Psi and Psi-2s nuclear modification factors. It emphasizes the need for further investigation into the mechanisms affecting these states, including shadowing, anti-shadowing, and final state effects. The research also emphasizes the importance of considering the role of cold nuclear matter effects, as well as the impact of the quark-gluon plasma on quarkonium production.